Last time we started section 3.3, multiplication and division of whole numbers, and we had gotten to the point where we looked at the three models for multiplication. Just a real quick run through about those. This was an example of repeated addition, and multiplication is sometimes even defined as repeated addition. We think about it sort of as almost like this is our definition for it, kind of like we think of subtraction, the definition being take away. It's not really, but we kind of think of it that way. Another model is an array model, and so you guys are going to get to think really quickly here in a minute here of things that you see in your everyday life that are already displayed in arrays or that you put into arrays. This was an example, I think it was cookies, yeah? And then an area model being almost like an array model, it just uses measurement of something, distances, lengths, things like that. So what I want you to do in your groups right now is to create one example word problem of each of those three. You don't need to solve it, you're just creating a word problem example of a repeated addition, an array, and an area model for multiplication, okay? All right, so somebody has an example for us for repeated addition. Which one? Melanie? I'm sorry, Abby. Sorry, you're in the same spots and stuff. Yes. Abby? Yes, I do know your name. Okay. Abby. I said it earlier.
Anna spends $3 every day for lunch. How much money will she spend from Monday to Friday?
Cool. Very good. What you guys have?
Zach can be line leader if he can get 3 stickers a day through Friday. If there are 5 school days in a week, how many stickers must Zach get to be line leader?
Excellent.
We're just doing Monday through Friday.
Everybody likes Monday through Friday, school week, right? All right, one more example of repeated addition. Amy.
At Chuck E. Cheese, students won 2 tickets at every game they played. If the students play 5 games, how many tickets does they win?
Good. That's good. All right, that was 3 repeated additions. How about 3 arrays? Somebody have an array problem that they would like to present? Yes, ma'am.
During a cheer competition, the cheerleaders are lined up 3 girls wide by 10 girls long. How many girls are there? A lot of girls.
Very good. Yeah, that's a good example. I heard you guys talking about yours, so do your array one as well.
All right. Tony has a box of crayons. If the crayons are organized 3 crayons wide and 8 crayons long, how many crayons does this box hold?
Good. Yeah. All right, how about one more array model? Anybody have something interesting they'd like to share? All right, go ahead.
A student can fit 5 letter tiles across their desk and 6 going down. How many letter tiles does the student have?
Cool. Okay, so we got letter tiles. You guys didn't choose anything that are the ones that I always hear. It's very interesting. I usually hear things like soda pop cans or toilet paper, stuff like that. Interesting. Okay, how about area? Have some area examples? At least 3 of you are going to tell me your area examples. Ashley's got one that she really wants to share. So.
Okay. Timmy wants a pet elephant. His parents tell him his room isn't big enough. If his room is 8 feet long and 10 feet wide, what is the area of his room, and should he get an elephant?
She got to the end of the course. She was like, wait a minute, I really didn't need the elephant problem.
So we added
It's okay. So should he have an elephant? All right. What else do we have for area?
We had, if Amanda's carpet is 3 feet by 5 feet, what is the area of the carpet?
Okay, cool. What else?
Francesca is building a dog fence. The fence is 4 feet wide and 5 feet long. How much area does the dog have to live in?
So to be careful with fencing because it has this 3rd dimension, right? So I think you mean like the space it takes up along the ground because you're saying it's like 4 feet wide. The fence is 4 feet wide. And what do you say? 5 feet long. So you just have to be really careful when you're wording things that have that 3rd dimension that you don't get the height involved by accident. Do you see what I'm saying?
Like the base too, like if we did the base of the doghouse,
Mm-hmm.
because would that be also talking about the height? Like keeping that into account?
Well, if you do the base of the doghouse, like how much square footage or how much floor space, you could use those kinds of language to be real clear about it. Yeah. So I'm not saying it's not okay. You'd have to be really careful when you're talking about 3-dimensional objects to make it work. Read it again for me, Leah.
Francesca is building a dog fence. The fence is 4 feet wide and 5 feet long. How much area does the dog have to live in?
I think it's okay the way you've got it worded. Yeah.
Just be careful.
Yeah, just be careful with the
Can you say-
3-dimensional stuff.
Can you say this feet by this feet? Or
Uh-huh.
is that kind of, okay.
Yeah, that's okay. You can do that. All right, does anybody else have an area one that they'd like to share? Okay. Let's see. We're going to take a look then at whole number properties. We're gonna do this one more time with division, so that you guys are gonna stay put for a little bit. Whole number properties. So these are properties now for multiplication. You'll notice some of them look quite familiar because we did them for addition, and they just have a different sort of a flavor to them with multiplication. Closure. For all whole numbers A and B, A times B is a unique whole number. Okay, so I know closure is one of those things that sounds kind of simple and it sounds super complicated all at the same time. It sounds like, well, yeah, of course, but then when I start really looking at things that are closed and aren't closed, it feels a little awkward. But all it's telling you is that when you multiply two whole numbers, you get a whole number. And that's true, right? You can't multiply two whole numbers and get a fraction, or multiply two whole numbers and get a decimal. That doesn't happen. It's another whole number. Commutative property says that the order in which you multiply doesn't matter, right? 5 times 2 is 2 times 5. Okay, that's what commutative means. We can multiply in a different order and it's okay. So we have that for addition and we have it for multiplication. We did not have it for subtraction, right? The order of the subtraction did change the value. The next one is the associative property. The associative property says that for A, B, and C, A times B, that quantity, times C, is the same as A times the quantity B times C. Okay, so again, the location of those parentheses, when it's all three numbers are being multiplied together, it doesn't matter the order in which you multiply. And that's actually a really helpful and good fact because sometimes it's very easy to multiply certain numbers in a series of numbers and not so easy to multiply others. Maybe to multiply it up, you have 2's and 5's in there somewhere, so when it multiplies, it becomes a wonderful 10. So you're like, oh yeah, I want to multiply the 2 and 5, and then I'll work with that because it's an easier way to do it. All right, identity property says there's a unique whole number 1, such that for every whole number A times 1 is equal to 1 times A, which is equal to A. We had a unique identity for addition. What was it? 0. So here's the catch. Whenever you're identifying properties, you need to make sure that you say that it is the multiplicative identity. I didn't say that very well. Multiplicative identity or the additive identity, because they're different. Commutative is the same thing, right? You're just switching the order, but identity involves a specific number. So you have to identify which it is you're using. Okay? A couple more. 0 property says that if you multiply by 0, you get 0. And it doesn't matter in which order. A times 0 is equal to 0 times A. And that's, of course, happening because it is commutative. And then we talked, Emily had asked last time, I think it was, about the distribution property. We actually get it now because in order to use the distribution property, you have to actually have two operations. You have to have addition and multiplication or subtraction and multiplication. So for all whole numbers A, B, and C, A times the quantity B plus or minus C is AB plus or minus AC. So you have that distribution property which relates the addition and multiplication together or subtraction and multiplication together. All right, so what I'd like for you to do is, I know you're in pairs right now, but go through this list. There are 6 of them. Yeah, there are 6 of them on this list. I want you to identify which property you believe it is. And then after that, I'd like for you to compare with those who are in your group to make sure that you all agree. Okay, and then we'll check all together and make sure everybody has the right things. Once you've completed them all yourself, compare with your partner or partners.
So I think we're all. Is it possible for you to change properties?
I don't think I have any that are two properties written down.
We're talking about, I got.
I think that they're intending you to do distribution because you don't see the times one part. You're not seeing the dot one.
So it's distribution.
It's which one?
It's supposed to be distribution.
I don't think so. I don't think that's what they're expecting for you to use on that one. Yeah, multiplicative what? Identity. That's your keyword there. Yes. Mm-hmm.
I did distribution again. I have like they took because it's kind of more like 40.
All right, what did we get on the first one on A? What property is part A? It is the zero property. How about the second one, part B? That is commutative property. Don't look at things and think, just because I see parentheses, it must be associative or distributive. It doesn't have to be. How about part C? That one is the associative property. All right, so what did you guys get for D? Yeah, it's the multiplicative identity property. Yeah, that'll be okay. Identity property multiplication is fine. How about E? That one's distributive. And F? It is a property, actually, yeah. It's funny looking. Huh? Yeah, they're equal. Uh-huh. So it's the which property? Those of you who saw it? It's distributive. I'll show you just a second here, Abby. Oh, you can keep going. Yeah, but it was to be like, this would be like one step of the problem. They've actually taken this piece right here and distributed it to each of those pieces. So it's 1 plus 2 times 3, 1 plus 2 times 4. So you see that there's that 1 plus 2 right here, right? And it's times the 3, and then 1 plus 2 times the 4. It's awkward, and you don't really think to do it that way when you're doing a problem. But if you were doing it with variables or something like that, you might. Yeah. All right, you guys ready to take a look at division? Any questions on this before we go on to division? Okay, then. Division of whole numbers. For any whole numbers A and B, where B is not 0, A divided by B equals C, if and only if C is the unique whole number such that B times C equals A. A is called the dividend, B is called the divisor, and C is called the quotient. So I'd like to take this language right here and talk about it with numbers. Okay, so like let's say we had 6 divided by 3, which is 2. The reason this is true is because 2 times 3 equals 6. Right? And that's, again, we kind of do subtraction the same way. We define it in terms of addition. This is the same thing for division. The way that we learn to divide as a child is that we reverse our multiplication facts in our mind. You've already memorized those multiplication tables. You've spent time on flashcards or doing computer programs and skill drills and things like that. And so if we can just use those facts we already know and we can reverse them, then we can save ourselves time for having to memorize something brand new. So this is the actual definition for division, is that it can be written in terms of multiplication. Now, there was a condition here. It said that B cannot be 0. Why? So let's see what happens. If I write down 6 divided by 0 equals, we'll just say k, it's equal to something, say. What would happen if I rewrite it with multiplication? I would get what? It would be 0 times k is equal to 6, right? What's the problem with that? It's not possible, right? I can't take 0 and multiply it by something and get back to 6. That's actually the reason that we can't divide by 0. It's undefined because it's not possible to multiply something by 0 and get a different number back. It would be actually ruining the 0 property that we have. So that's actually why that's in there. Those languages you've probably heard before. A is the dividend, B the divisor, C the quotient. Quotient is probably the one that we use the most when we're talking about division at the younger ages. All right, there are 3, I think it's 3, maybe it's 4. It's 4. There are 4 models for division. The first 2 are actually kind of grouped together in your book. I separate them out because they do have a different flavor to them, each of them. The first one says, this is the set partition model. Junie has 24 rocks and she wants to give them to 6 of her friends. How many rocks will each friend get? So the idea with this one is to take the 24 rocks and to partition them among the 6 friends. So we're wanting to take 24 rocks and put them into 6 groupings, right? So physically what you would probably do if you were a young child is that you would do this. You would go 1 for you, 1 for you, 1 for you, 1, all the way down, right? And we do it again. We go through like this. But that's what we would do. We would put them into groupings of 6. And if you think about it, this is actually what you do in a classroom when somebody says number off by 6s, right? What the teacher is doing or the leader is doing is they're fixing the number of groups they're going to have to go between as the leader of that session. They want to make sure that they've got enough time and ample, opportunity and whatever, that when they put you in these groups, there's only 6 groups, something like that. So in terms of drawing a picture, we actually end up with these 6 groups of 4, right? Okay, I think I've got 6 groups of 4. Here is 1, 2, 3, 4, 5, and 6. I have 6 friends that are going to get groups of rocks. And how many rocks will each friend get? 4 rocks. Now, that's a little bit different than the next model. We're still talking about our 24. All my problems have 24 rocks in them, just so you know. Junie has 24 rocks. She bags them together in groups of 6. If she gives one bag to each friend, how many friends will receive a bag of rocks? There's really something quite different in the way that this problem is worded. The difference is that she's not controlling how many friends get the rocks. She's controlling how many rocks each friend gets, right? Do you guys see that? In the last example, she was controlling how many people got the rocks. And in this one, she's controlling how many rocks each person gets. You can't control both. You have to pick one. So in this case, she's got her, let's see, groups of 6, right? So I need to have a couple more of these. All right, so here's a group of 6. So this is one bag of 6 rocks. There's our second bag of 6 rocks. Third bag. Apparently I got little rocks as I kept going. And in total, that's 24 rocks if I count them all up. How many, and they're grouped together, so something like, if you will, I've got one bag of 6, I've got this bag of 6, that bag of 6, and this bag of 6. So how many friends get rocks if she controls this way? Yeah, 4 friends. The answer is still the same, that is the numerical value, but it's actually answering a different question, right? This is 4 friends now instead of 4 rocks, which is what we were answering before. A couple more. You'll notice again that we have the same problem, basically. We've got our rocks. Junie has 24 rocks. She wants to give them to 6 of her friends. How many rocks will each friend get? This is a missing factor. okay, approach. So I want to show you what the missing factor approach looks like. So with missing factors, we're going to write down 24. We're dividing by something to get something else. This one says Junie has 24 rocks. She wants to give them to 6 of her friends. So this is 24 divided by 6 equals our question mark. Okay? You could also write it, and it would be fine if you did 24 divided by question mark equals 6. Either direction that you write it, what you're going to do is you're going to change this problem to be a multiplication problem. This is like the definition of division, excuse me. So this is going to say 24 equals 6 times what? This one's going to say 24 equals what times 6? Right, they both change to the same thing. And the question is to fill in the missing factor using what you know about multiplication. And the missing factor would be 4. And so the answer is 4, and again it's rocks, because this time we knew the number of friends. How many did they each get? 4 rocks. Okay, last example. Repeated subtraction. Junie has 24 rocks. She wants to give them to 6 of her friends. How many rocks will each friend get? Are you guys done with rocks? Very done with rocks. Okay, here's why this works. Repeated subtraction is actually a pretty cool algorithm. It works really well. For those of you who are going to do special ed in some sense, I've seen this used quite frequently with special ed kids. So the idea is that instead of actually using the division and multiplication facts as they're related, you're using division as it relates to subtraction. So here's the way this works. If I physically had a child who gave away 1 rock to 6 people, how many rocks did they give away? 6 rocks, right? So I would subtract off 6 rocks. As the child giving them away, I now do not have 24 rocks in my hand anymore. I have 18. And then I would do it again. I would give each of my 6 friends a rock, leaving me with 6 fewer rocks for a total of 12. And then I would give again each friend a rock, 6 rocks, leaving me with 6. And then I'd give each friend a rock, leaving me with 0. The answer to this question then is how many times I subtracted 6. Because every time I subtracted 6 was a time when I gave each of my 6 friends a rock. So how many times did I subtract 6? 4 times. So that each friend got 4 rocks. Now, some benefits and some drawbacks on this one. The benefit is I do not need to know how my multiplication facts are working in this particular problem. That's a benefit for a child that struggles with memorization, things like that. Okay, that's a basic thing that's going on in this problem that's to be aware of. Something else you should be aware of is if the number were quite large, like not 24, but like 124, this would be a very long process, right? We'll talk about what we do with this process when the numbers are larger when we get to section 3.5, I think, 3.4, 3.5. Okay, we're going to talk more about how we do repeated subtraction with bigger numbers. So there is a way to deal with it that still has some of the same feel to it, but it's bigger numbers. But even with the smaller numbers, this still could be a tedious process. I have to subtract many times, okay? And then every time I subtract, I might make an error. So there's some good and there's some bad. Also be aware that I don't have to have a remainder of 0 when I'm done. Like I didn't have to evenly go in. Maybe I started out with 25 rocks, and so when I'm done, I still have 1 rock, okay? So there's nothing special about it, like, oh my goodness, it didn't end with 0, I must have done something wrong. No, not necessarily, okay? So there's nothing special about that. All right, so what I would like for you to do is to notice the note here. 3 of the 4 models above do not represent different types of word problems, as they did with subtraction, for example, or multiplication. But rather they represent different ways of solving the same word problem. Did you guys notice that? Different ways of solving the same word problem. So what I would like for you to do is I'd like for you to create word problems and solve them with each of the 4 models for division. Note, 3 of the 4 problems will be the same. Okay? So the first 2, part A and part B, are going to be 2 different problems. Okay, so now I made mention of this when we talked about set partition, that we were controlling how many groups we had. And when we did part B, we were controlling how many people are in each group. So think about it when you talk about numbering people off in a class, right? You number people off in a class, you control the number of groups you have. But if I want to control how many people are in each group, I can't have you guys count to 10 and number off, right? That doesn't control that. That controls that I have 10 groups. So if I want you in groups of 2, I have to sort of say like you 2 work together and you 3 work together and however like that, okay? That controls that. And so that's the second one, this set partition model, the variation one. I'm partitioning, but I'm controlling the number in each group instead of the number of groups. So parts A and B are going to be different problems. They could be very related problems, like my rock example, but parts C and D are going to mimic exactly either A or B, whichever one you choose for them to do, okay? So you're going to create 2 word problems. What you're going to create then on the other pieces is you're just going to show the different ways of solving them. That's all you're going to do, okay? So go ahead and give that a try. Never mind, we will finish this up next time.